Hello, this is a short video to remind you about some of the right-hand rules you may have missed over the last couple of days. One, when you have a wire carrying a current, you'll have a magnetic field that forms a circle going around it. So picture this being the wire. You have a magnetic field going around it either clockwise this way or counterclockwise this way. And it depends on what's called right-hand rule. Picture your thumb being the direction of current. If the current were going up the wire, your fingers are going to go around this way, showing the direction of the magnetic field. It'll be a circle in the direction of the finger, so this way around here. If the current were to reverse, the magnetic field reverses. Another way to visualize it is this little diagram here. This shows the direction of the current is this arrow here, and these black arrows represent the magnetic field. So you've got your current coming out this direction. Magnetic field goes around this way. So see the fingers going the same direction as the arrows. So circular magnetic field around a long straight wire gives you the direction. At any given point, we'd say this magnetic field is that direction, here it's that direction, here it's that direction. We can say the overall magnetic field is, in this case, counterclockwise, but at a specific direction or specific location, give a specific direction. Well, the first right-hand rule was to determine the direction of a circular magnetic field around a wire that's carrying current. The second right-hand rule is for determining the direction of forces on currents or charged particles in a magnetic field. So, for example, if you have a magnetic field, check the notes online for diagrams. You'll see a bunch of X's or dots. Remember, the X's is a magnetic field going into the board, and the dots are a magnetic field coming out of the board. So a charged particle that is moving into this region will experience a force. The magnitude of the force of a charged particle is QVB sine theta, where theta is the angle between the velocity vector and the magnetic field vector. The direction of the force, this little diagram here helps. I is the current, that'd be the moving charged particle. B is the magnetic field direction, and this is the force on that particle. So if you had a magnetic field coming towards you and the current going that direction, the force would be down this direction. If we change the direction, so the current's this way, the charged particle is moving that way, magnetic field's that way, then the force would be this direction. Obviously, you don't have one of these in your pocket, and it would hurt if you did. Use the right-hand rule for this. Now, the textbook uses a fingers pointing like this, and they're representing these diagrams like this. But since I can never remember which one is which, I do it this way instead. I have the fingers as the magnetic field, and this is the velocity, the motion. Think of a hitchhiker thumb, right? That tells you direction. So here's the velocity, here's the magnetic field. So if the magnetic field were up and the velocity was toward my face like this, then the palm pushes. So your force is this direction. If the magnetic field were this direction, so the magnetic field is this way, the velocity of the particle is this way, the force is this direction again. So these two are determining magnetic field versus the velocity. Now that's a positive charge. A positive charge is pushed by the palm. A negative charge experiences a force the opposite way. So the back of the hand. So if my hand is like this, a positive charge would have a force this direction, a negative charge would have a force that direction. Now, because these charged particles are free to move in any direction, and the force is perpendicular to the motion, the force acts like a centripetal force. It'll cause the object to go in a circle. So while the calculation is QVB sine theta for the force on that charge, that could be set equal to mv squared over r, where that is your F equals ma. So the last right-hand rule, it's the same as the one with the charged particle, but instead it's on a wire. So if a wire is carrying a current and it gets near a magnetic field, then there's going to be a force on the wire. The direction of the current, we always consider it to be positive current. So the direction of the current and the direction of the magnetic field will affect the direction of the force. Exact same setup as this, where now I is definitely the current, B is the magnetic field, and that's the direction of the force. I can actually show that. Okay, we have a magnet. Back on the camera. So there's our magnet, and there's our wire. We take a loose loop of wire here and suspend it over the magnet. If I turn current on, you see that get pushed upward. Do that again. Wire gets pushed up by the magnetic field. If I reverse the magnet and turn it on, it gets pulled down. Again, pulled down. So those two together, and where you have the direction of the magnetic field, the direction of the current, and the force on that wire. So if we had a magnetic field this direction, the current goes this direction, again positive current, the force would be upward. If we had magnetic field this way, current this way, it'd be a downward force. So right-hand rule for forces on objects is the same for charges and wires. Still using right-hand rule, still using magnetic field and direction of current. The formula for the wire is Philb sine theta. F equals ILB sine theta. Some of the fonts look weird in the PDF that you see on Schoology. I don't know if the L still looks like an L. So the equation is F equals ILB sine theta. And I is the current, B is the strength of the magnetic field, F, of course, is the force the wire experiences. When I say L is the length of the wire, it's the length of the wire overlapping the magnetic field. If the field's bigger than the wire, just do the length of the wire. If the wire is bigger than the field, then do the size of the field. Do that part of the wire that is going through the magnetic field. Sine theta is, again, the angle between the vectors, the angle between the current vector and the magnetic field vector. So maximum would be when your wire was perpendicular to the magnetic field. If you have any questions, give us emails, come in before school, after school. Help you out.